So, in today's class, I am going to talk about non-homogeneous second order differential equations and how you can write a general solution of a non-homogeneous second order differential equation. We have already seen how to solve homogeneous differential equations, okay, or at least get solutions of homogeneous differential equations. If one solution is known, how you can get the second solution and so on. So, today I will talk about non-homogeneous equations. So, just to remind ourselves, so this non-homogeneous second order differential equation looks like this, plus y prime plus b of x y equal to c of x. This is the general non-homogeneous second order differential equation, and we want a general solution okay. So, a general solution means will have two arbitrary constants. So, it will have two arbitrary constants, okay, and this is what we want to get. So, we want to get a general solution of this equation, okay. Now, for the homogeneous case, so for corresponding homogeneous equation, and I'll just, so the corresponding homogeneous equation will look like y double prime plus a of x y prime plus b of x y equal to 0. So, for this homogeneous equation, okay, the solutions are denoted as y h of x and or simply y h, okay, and what I should say is that this is the general solution. The general solution is denoted as y h. So, I will use y h as the general solution of the corresponding homogeneous equation, okay. So, y h this will have two arbitrary constants, okay. We saw how we can get y h, okay, using linear combination of basis functions, okay. Now, what we want to do is to write a general solution for this non-homogeneous equation, okay, and that will also involve two arbitrary constants, okay. So, I will just state the way you write the general solution of the non-homogeneous equation. So, if y is a solution of the non-homogeneous equation, okay, then you can write y as y h y of x, I will just put y of x as y h of x plus y p of x. So, y h of x, okay, so y is a general solution of non-homogeneous differential equation. This is a general solution of y h is the general solution of homogeneous differential equation, and y p is any particular solution of the non-homogeneous equation. And when I say it can be any particular solution, the word any is very important. You can choose any particular solution and you can write the general solution as that. Okay. Now, if you remember when we did homogeneous equations, we said that you can write different bases for the same equation. You can write it in terms of different bases. So, same way, I mean, there are different ways to write the general solution, okay, and therefore you can choose any particular solution of the non-homogeneous equation, okay, and that will give you a general solution of the non-homogeneous equation. Okay, so just an example of this. So what is important is that we are getting a general solution of the non-homogeneous differential equation, okay, which will have, this will have two arbitrary constants. Now the general solution of the homogeneous differential equation will also have two arbitrary constants. But this particular solution will have no arbitrary constants. Okay. So I think it's best if we look at an example, okay, just to illustrate this point. Okay, so the two arbitrary constants for this for y came entirely from y h. Okay, so let's look at an example now. So suppose you have the differential equation y double prime plus 4y equal to 4. Okay, it's a simple differential equation, and in this case you can see that the general solution of this is given by y is equal to, so this is y double, so if you look at the homogeneous equation, so y h, okay, now this is homogeneous equation, you have y double prime plus 4y equal to 0, okay, and the general solution of that will be a sum of cos 2x and sin 2x. So I can write it as C1 cos 2x plus C2 sin 2x. So this is my y h, okay, it has two arbitrary constants. Now you need to find the yp, you need to find one particular solution, okay, and you see that there is a 4 on the right, okay. So if y equal to 1, then this term will become 4, okay, and y double prime of 1 is 0, so you will get 4 equal to 4. So particular solution yp of x, just choose as 1, okay, just by inspection. Okay, we will come later to show to show you how it is possible to choose this in a more reasonable way, but if you just use this just by inspection, we can choose this as the particular solution. So the general solution y looks like C1 cos 2x plus C2 sin 2x plus 1. That is the general solution of this differential equation. Okay, and you can verify this. Okay, so suppose you just substitute this in this equation. Okay, what you will get is exactly that, you can see that this will clearly satisfy this differential equation. So what we have shown is that how you can get a general solution of a non-homogeneous differential equation from the general solution of the homogeneous differential equation and one particular solution. Okay, now how do you choose? So in this case we just saw and we decided what yp was. So how do you choose yp in general? Okay, now the idea here is that you try based on c of x, based on c of x, which is the right hand side of non-homogeneous equation. So what I mean is, if your equation looks like y double prime plus a of x y prime plus b of x y equal to c of x, okay, this thing equal to 0 is your homogeneous equation, okay, and when it is not equal to 0, you have to worry about the non-homogeneous equation. So your choice of yp depends on what cx is, okay, and a general recipe to calculate yp is to choose it based on c or based on cx. So I'll just make a small chart here. So I'll write cx out here, and I'll write trial yp of x. So what I'll show you is I'll just make a chart with various choices. So suppose my cx looks like e to the ax, e to the some constant times x. Okay, then my trial will also be some some c e to the ax. So, you just take e to the ax multiply by some constant, that will be my trial function. Okay. Suppose on the other hand, if my Cx looks like x raised to n, okay, then my trial function will look like a polynomial in n. So, I take it as I will take it as C1 or C0 plus C1x plus C2x plus up to Cn x raised to n. If my C of x is just a power of x, okay, I try with these constants and then I substitute in the equation and then I will find out what the values of these constants should be. Okay. Similarly, if you have sine omega x or cosine omega x, okay, in either case you just take your trial function as C1 sine omega x plus C2 cosine omega x, okay, and then you substitute in the differential equation and then you find out the values of C1 and C2. Okay. If you had a product of e to the ax times sine omega x or cosine omega x, okay, then again your trial function will also look like e to the ax, and then you have a sine omega x plus b cosine omega x. So, you try this form, okay, and you substitute in this equation and then you calculate your the values of a and b. Okay. So, what I am showing you here is a recipe of how you choose your particular solution, okay, just by looking at what your form of Cx is. Okay. Now, this works often, okay, but there is also a more and we will see examples. This is a very practical method. So, I will emphasize that this is a very practical and useful method. Okay, because and it works quite well. Okay. However, a formal method, okay, of calculating yp is what is called variation of parameters. So this is a formal method. Okay, no trials. Okay, so no trial function. So you don't use any trial function. Okay, you just take whatever your C of x is and you solve this. Okay. So let us take an example or let us see what the formal method is. So the formal method is suppose your y h of x, okay, is equal to, this is solution of homogeneous equation, the corresponding homogeneous equation. Suppose this solution you wrote it as a form C1 y1 of x plus C2 y2 of x. Then the non-homogeneous equation dE solution, what you write it is, you write it as y of x is equal to u of x times y1 of x plus v of x times y2 of x. So instead of just C1 and C2 being constants, for the non-homogeneous equation you imagine that you replace it by some function u and this by some function v. So again once you do this, then you have to calculate what is u and v. Okay, so this is just like the variation of parameters that we used in the case of first order differential equations. So if you take this and substitute, okay, in the original differential equation, okay, what you will get, so let us just work out what happens when you substitute. So you will get y prime is equal to u y1 prime plus u prime y1 plus v y1 y2 prime plus v prime y2, and then you calculate y double prime, okay, that will be u y1 double prime plus I will write it 2 u prime y1 prime plus u double prime y1 plus v y2 double prime plus 2 v prime y2 prime plus v double prime y 2. Okay, so you have this, and when you substitute this in your non-homogeneous equation, okay, then what you will get is that your instead of y double prime you have all these terms. So you have u y 1 double prime plus 2 u prime y 1 prime plus u double prime y 1 plus v y 2 double prime plus 2 v prime y 2 prime plus v double prime y 2. So this is your y double prime, and then you have plus a of x into y prime. Y prime is nothing but u y 1 prime plus u prime y 1 plus v y 2 prime plus v prime y 2. Okay, so remember this whole thing was your y double prime, okay, a of x times y prime, and then you have plus b of x times y is nothing but u y 1 plus v y 2 equal to c of x. Okay, so what we did was we just took this trial form of y, okay, and we substituted in this differential equation. Okay, now you have to look at it term by term, okay, but what you will see is the following. What you can see immediately, remember y 1 and y 2 are solutions of the homogeneous equation. So y 1 and y 2 satisfy the homogeneous differential equation. So you can see that if you look at this term, look at b times y 1, okay, so there is a u in front, okay, then you have y 1 double prime with a u in front, and then you have a times y 1 prime with a u in front. Okay, so these three terms are just u times, so if I just write this as u times y 1 double prime plus a of x y 1 plus b of x y 1. Okay, so that is what you get when you add these three terms that are underlined in light blue color. And now you can see that the term in the bracket is equal to 0 because y 1 satisfies the homogeneous equation. So these three terms add up to 0. Similarly, you can look at this term, and then you can look at the corresponding terms here, which looks like this, and here you will have a term v y 2 double prime. Okay, so those two also add up to 0. Okay, so then what you are left with after this is the following. You are left with an equation that looks like this. So you have 2 u prime y 1 prime plus u double prime y 1 plus 2 v prime y 2 prime plus v double prime y 2. This is equal to plus a of x times u prime y 1 plus v prime y 2 equal to c of x. Okay, so notice when we did this, we got entirely rid of the b term, okay, and we are just left with this. Okay, now actually even this itself is not that straightforward to solve, okay, because you have u and v, okay, and in general you cannot solve this straightforwardly, okay, but you can do one thing. You can look for solutions. So here is a trick that we use. So we look for solutions that satisfy u prime y 1 plus v prime y 2 equal to 0. So this term that multiplies a will go to 0. Okay, so we look for solutions that satisfy this identity. Okay, and now so what this gives you is the following two equations. So the first equation is u prime y 1 plus v prime y2 equal to 0, and the second equation, okay, looks like so now my second equation will have the form 2 u prime y1 prime plus u double prime y1 plus 2 v prime y2 prime plus v double prime y2 equal to 0. So, this may look a little complicated, okay, but actually the solution of this is fairly straightforward. Okay. Now, once you impose this condition, so if you take the first derivative of the first equation, so let me call this equation 1 and let me call this equation 2. Okay. So if you take first derivative of 1, okay, then you get u double prime y1 plus u prime y1 prime plus v double prime y2 plus v prime y2 prime equal to 0. Okay. And you can see that in this equation you have in the second equation you have u double prime y1, and instead of single u prime y1 prime you have twice u prime y1 prime. Okay. So now if you just subtract the second and third equation, so if you just subtract equation 2 minus 3, okay, then you get u prime y1 prime plus v prime y2 prime equal to 0. Okay. And let me call this equation 4. Okay. Now, if you just look at 1 and 4, now this looks like u prime times y1 and v prime times y2, u prime times y1 prime and v prime times y2 prime equal to 0. Okay. Now, you can immediately so this should be equal to, sorry, this is not 0, this should be c of x, this should be c of x. This quantity, remember, was equal to c of x. Okay. So, and now from the first derivative what you will get on the right hand side is not 0, but you will get d by dx of c of x. Okay. So, so finally what you get is this is equal to dc of x by dx. Okay. And this is very nice, because what if you look at 1 and 4, okay, they if you just look at these two, then using your matrix methods you can write u prime is equal to, in terms of determinants, so what you will get is 0, I will just call it c prime, and then you have y2 prime. So, this determinant divided by y1 y2 y1 prime y2 prime. Okay. So, what I did was I just looked at 1 and 4 as as a system of linear equations for variables u prime and v prime. Okay. So, then you immediately get this, and you also get v prime is equal to, you will get y1 prime 0 c prime, and you will get y1 y2 y1 prime y2 prime, should just be c of x. Okay, this should not be dc by dx, this should just be c of x. Okay, so because we took a derivative of 1. Okay, so what I wanted to emphasize is that this should be c of x. Okay, and so I get my u prime and v prime in this form, and you can write u as the integral of this whole thing. This denominator, okay, so the denominator is referred to as w, or the Wronskian. Okay, and this is basically y1 y2 prime minus y1 prime y2. Okay, and so you can write your your u and v in the following form. So what you will get is u prime is equal to minus cy2 by w and v prime is equal to cy1 by w. Okay. And so what this variation of parameters gives you, it gives you u equal to integral minus cy2 by w dx and v equal to integral cy1 by w dx. Okay. So we can get, so we calculated u and v, okay, and this basically, so once we have u and v, we can write y is equal to u y1 plus v y2. Okay. So we have solved non-homogeneous differential equation. Okay. So if you know y1 and y2 of the homogeneous equation, then you can solve the non-homogeneous differential equation using this method of variation of parameters. Okay. So in the next class I will discuss some practice problems, okay, and then in the next module, that is the following week, we will start looking at how to get the solutions of the homogeneous equation, what is the general method of getting the solutions of the homogeneous equation, and this will lead us to something called the power series method.